is in this. Unless you consider.
Yeah, that's how.
All right, so the idea of a limit was really that the concept was really what brought mathematics kind of into the modern era, to coming up with a solid technical definition of a limit, and that's what finally gave calculus a rigorous foundation, because before we had a firm idea of what a limit was. It was kind of, things were kind of defined in a very squishy way, and limits made it not squishy. Our idea of a limit for a function of two variables is very similar to the idea of a limit with a function of one variable. So the idea with a limit, the general idea is if our function is, if we have a limit, we can say how close we want to get to a particular range value, a particular function value, and we can find an interval in the domain that guarantees us that we're within that distance of a particular number in the range value. So the idea is if we want to be close together in the range, we can find an interval in the domain that guarantees us that we're that close in the range. So the limit is how we define technically what we mean by close together. So let's talk about our definition. This should be, it will sound familiar, and then we'll talk about what it means. So we're going to say f of x, y is a function of two variables. We can make it more, and we just extend it the way you would expect. So we have a function of two variables. And L is a real number. The limit as xy approaches x0, y0 of f of xy equals L if for any epsilon greater than 0, and I like to include no matter how small, there exists a delta and our delta is greater than 0, so that 0 less than the square root of x minus x0 squared plus y minus y0 squared is less than delta. This implies that f of x, y minus L is less than epsilon. Now this quantity, x minus x0 squared, y minus y0 squared, square root, in 2 dimensions, that takes the place of the absolute value of x minus x0. Because what is this square root of x minus x0, y minus y0 squared, square root? Isn't that just the distance between xy and x0, y0? That's the distance formula. So what we're saying here is if we want our function value to be close to the limit, close to some L, and this epsilon can be as small as we want, if the function has a limit, then we're guaranteed that we can find some delta value, so that if our x0 and y0, or x and y are close within that distance of x0, y0, that guarantees us that our function is within epsilon of our limit. I'm going to draw a picture here in just a second. We call this quantity the square root of x minus x0 squared plus y minus y0 squared is less than delta, is called the delta neighborhood. About x0, y0. Or we can call it the open disk. About x0, y0 with radius delta. Because if we square both sides here, then this equation of a circle, x minus x0 squared plus y minus y0 squared is less than or equal less than delta squared. So it's all those x, y values that are in that within that circle. When you go into higher dimensions, you call this not an open disk, but you call it an open ball, because you're talking about a sphere. And then higher dimensions, you just talk about a higher dimensional sphere. So the idea of limits is very friendly, right? We have a neighborhood, we have a ball. It's great. All right, so let's draw a picture of what we mean, so we can see visually what this definition tells us. So we're not going to use the limit definition of, or the epsilon delta definition of limit a lot, but I want you to kind of understand in general terms what it means. We want to be close to the value in the range. We have to be guaranteed that we can find a distance in the domain that gets us there. It's kind of like setting a machine. We want a machine to have certain accuracy, so we have to be able to set the dial to a particular accuracy before we start to get the result that we want. So this delta is how we set the dial. We're guaranteed that we can set the dial to a certain precision to get a certain precision out of the machine that we're looking at. All right. So graphically, our delta neighborhood, I'm just going to draw our delta neighborhood in the plane, and then we'll draw a three-dimensional sketch here. So get a circle here, and we'll make it dotted like so. There's x0, y0. The radius of this is delta. Notice that our boundary is dotted. We're not including the boundary. And everything inside here is where the square root of x minus x0 squared plus y minus y0 squared is less than delta. So that's our delta neighborhood inside that little disk, inside that circle. And in 3 dimensions, what we're looking at is we have some surface up here. There's z equals f of xy. My students last year said that the generic surface was a blanket. Just draw the blanket. All right, so we have our open disk here in the xy plane. And there's x0, y0.
Are we projecting it?
That's obviously the open ball.
That's the disk. That's his disk in the xy plane.
How does it relate to the, is it like the shadow?
No, this is just this open disk. Now we're going to project this up onto the surface. So this is our circle in the xy plane. We're going to project it onto the surface.
No, Bobby, that's a circle. It's supposed to be a circle. On the
Yes.
XY plane.
That's a circle in the, my computer is,
Like a cookie cutter, Kevin. You blanket.
yes, this is this circle in the xy plane. So we get some strange shape up here on the surface when we project it up onto the surface. This minimum height of this shape on my xy on the surface is f minus or L minus epsilon. This height, the maximum height here, is L plus epsilon. And right here in the middle is L. So we're saying that for our limit to exist, and there's some point x0, y0. Sorry, xy. So for our limit to exist, we have to be able to find this disk in the xy plane such that when I take the minimum value of the function, when I project that up onto the surface, and the maximum value, both of those are within epsilon of the limit. So that's what our definition is telling us. And if our surface behaves strangely there's some kind of jump, step, a gap, then our limit's not going to exist.
So the thing down, the original x0, y0 thing, even though it doesn't look like a circle, it was a circle originally.
Yes,
You
if I
project the circle.
if I turn this horizontal, it would look like
It would
this.
look like that.
Or vertical. If I turn that plane vertical, you'd have a circle. So it's sideways, so it kind of looks like an oval.
So epsilon can be anything, right? So it just means that it can't like jump to like a random place.
Right, right. If we said we wanted to be within 0.1 of L, but we had some kind of big gap in our function, then our function value we couldn't find a disk in the domain that would guarantee us that from here to here we're within 0.1 of L. All right. So a couple of important differences for limits, for multivariable limits and single variable limits. First, there is no multivariable L'Hopital's rule.
Oh, I'll come up with it though.
So you can't just take derivatives to find your limits. Sometimes you can make a substitution and turn your multivariable function into a single variable function. You could substitute x squared plus y squared equals r squared. So you can make a substitution and then use L'Hopital's rule. But in general, there's not a L'Hopital's rule for a multivariable function. So be aware of that. Students always want to use L'Hopital's with multivariable functions, and there is not a L'Hopital's rule. Second, with the single variable function, we just had to worry about the limit from the left and the limit from the right. We just had to worry about two directions. Here we have to worry about every direction. So our limit must be the same from any direction. It can't be just from the left and from the right. It has to be from any direction. And sometimes functions are very strange. Well, we saw an example last time. One of the pictures, the Mathematica pictures I showed you, there was a function that was discontinuous on a parabola. So that function would be continuous everywhere except for that particular parabola. So if you approach your point on that parabola, your limit's going to be undefined. From anywhere else, you can come up with a limit. So we can't just say from the left and from the right. We have to think about any direction. All right, we good so far? Okay. All of our rules, our usual rules, for sums, products, etc., still hold. So the limit of a sum is the sum of the limits. The product of a limit is the limit of the products, etc. A couple of important ones that I want to emphasize are the limits of polynomials and rational functions. So a polynomial, a multivariable polynomial is just going to be something with positive powers of x and y. Rational functions are going to be made of quotients of functions that have positive powers of x and y. So x squared plus xy plus y squared is a polynomial because we have positive powers of x and y. For limits of polynomial and rational functions, the limit as xy approaches x0, y0 of f of xy is f of x0, y0. So for polynomial and rational functions, we find the limit by plugging in our variable values. So polynomial and rational functions are nice. It can.
So you have to deal with that.
So then we have to do more work, just like with a rational function of a single variable. And I'm going to say equals where defined. And we'll talk about how we do more work with rational functions in just a second. In general, we can find the limit of a polynomial or rational function just by plugging in our point that we're interested in. All right, so what we want to do is use limits then to talk about continuity. We want to know when our multivariable functions are continuous. So let's talk about continuity. Our definition of continuity is going to be exactly like it is for a single variable function. F of xy is continuous at x0, y0 if the limit as xy approaches x0, y0 equals f of x0, y0. So we're leaving out a couple of things here that are implied by this definition. Our function has to exist at the point. The limit has to exist. The fact that we're saying that's the limit exists. And the limit has to equal the function value. Just like for a single variable function. And our usual rules for continuity still hold. So I can add continuous functions and get continuous functions. I can multiply continuous functions and get continuous functions. I can find the quotients of continuous functions and get continuous functions where those quotients are defined. So our usual rules still hold. And the fact that our usual rules still hold, that implies that polynomials and rational functions are continuous. And they're continuous where they're defined. Well, we want to be able to look at functions other than just polynomial and rational functions. We want to be able to look at more interesting functions. So we need to talk about composite functions. That's how we make up more interesting functions. So we talked a little bit about composite functions the other day when we talked about multivariable functions. We're going to say that z equals f of xy is continuous. So we have a continuous multivariable function. And g of z, so a function of a single variable. And this is a continuous function of z. So f of xy is a multivariable function. Our output is a single variable. And g is a single variable function, and we're plugging z into that function. If this is the case, so we have the continuous multivariable function, a continuous single variable function, then g of f of xy, and that's the same as g of f of xy, is continuous. So compositions of continuous functions are continuous. And the limit as xy approaches x0, y0 of g of f of xy is g of f of x0, y0. So what this tells us is that functions like e to the x minus y cosine xy over x squared plus 1, the natural log of 1 plus x squared plus y, or x squared y squared, etc., are continuous. Where defined. So we can make interesting functions, these polynomial, rational function, quotient of polynomial. So we're making a composition of a continuous function, e to the x, cosine x, natural log x, composing continuous functions, so we get continuous functions. All right. Questions? Well, let's take a look at some functions and talk about their limits and their continuity. So your homework, you'll get some problems in your homework. You might see a problem like this on a quiz or a test. It will say discuss the continuity. That just means determine if the function is continuous, if there's any problems with its continuity, and then find a limit if it exists. So discuss just means do the work to figure out if it's continuous. So we want to talk, for these examples, we want the continuity and the limit as xy approaches 0, 0 for all of these functions. So yeah, in your book it would say discuss the continuity and find the limit. F of xy is e to the xy. We're going to have any issues here with our function being undefined or some strange values popping out of there? No? So this is going to be continuous. This is a composite function. This is going to be continuous everywhere.
What would be a strange value that would make it not?
1 over 0, something like that.
Okay.
Natural log of 0. Continuous everywhere. And the limit as xy approaches 0, 0, limit is 1. Any ideas what that function is going to look like? It's not a super complicated function, but it's sometimes with these multivariable functions kind of hard to visualize. Let's take a look. There's e to the xy. E to the x times y.
So it's like a logarithm thing or the exponential thing.
Exponential thing, but look, we have this interesting little rise here. So right along the middle here, rises up and back down. And these, where it's cut off here, and these flat surfaces, it will continue to go up like that. And here, it would just flatten out.
So that's not like a cusp.
Well, not a cusp, no. But we'll talk about how we find those interesting points in a little bit, in a couple of sections. All right, let's look at number 2. F of xy is x squared over x squared plus 1 times y squared plus 1. Polynomials in the numerator and denominator. Are we going to get any problematic values? No, because our denominator can never be 0 because we just have those quantities squared. So this is going to be continuous. And our limit as xy approaches 0, 0, 0.
Is it not continuous everywhere?
Yeah, it's continuous everywhere. I just wrote continuous. Continuous means continuous everywhere. All right, let's take a look at that one. This one, not off the top of my head, I'm not sure. So there's that one. Yeah, and we get this interesting thing happening here at 0, 0, 0. And I believe this one's horizontal all the way across there. So that's an interesting looking surface.
Oh yeah, as long as x equals 0, I was writing 0.
Right. As long as x equals 0, it's going to be 0. All right, number 3. f of xy equals 1 minus cosine of x squared plus y squared over x squared plus y squared.
Oh, that's not.
Yes. No.
What about this one? Not continuous. Where's our problem?
0, 0.
Not continuous at 0, 0.
Since that's only one value, it would just be a single point that's not continuous.
Right.
If we just had it as like not continuous at all x when it's equal to 0, would we have like a line or something?
Mm-hmm. And we'll talk about one like that in just a little bit. Guesses as to what this looks like, or what's our limit?
Negative.
Well, cosine of 0 is 1, and 1 over 0 is undefined. So limit is undefined. Limit does not exist.
If it's non-continuous, this does not.
All right, ideas about what this looks like?
Probably gonna mess up something.
Well, what do you think this x squared plus y squared quantity is going to give to our surface? Guys, we're going to have something to do with circles.
Circular cosine function.
And this, so let's take a look.
It'd be really bumpy.
It's going to be really bumpy.
And it goes like this, and then it goes like this.
Oh,
Whoops.
That's not it.
There, I'm out of order. There it is.
It's like a swerve.
So it's like if you did a cannonball in the swimming pool. You get this huge splash. The splash is so huge. These
Areas are undefined.
these things would continue to go up and down to a height that's larger than any value.
So would this be like an oscillating function kind of situation?
Sort of, yes. But see how we get this? It's really curvy, really bumpy here, especially as we get close to 0, 0. Yeah, so that's an interesting one.
It's like you see rocks in pottery.
All right, let's take a look at one more, and then we'll talk about one where we have discontinuity at more than just a point.
This is just laws. There's like a 1 minus cosine x squared plus y squared.
How about the natural log of x squared plus y squared?
I saw it in the
Right, we're going to have a problem at 0, 0. So it's going to be not continuous at 0, 0. And so our limit as x, y approaches 0, 0 is not going to exist. All right, and we kind of saw a quick glimpse of that one. What is this x squared plus y squared going to give us? Circles. So our level curves are going to be circles here. So let's go back here, and I'll go back 1. There it is. We get kind of this infinite funnel shape.
It's like the toilet full of water
That same shape.
I think of it as, you know, those things, novelty things where you put a penny in
Oh,
and it rolls down.
Those gravity wells.
That's kind of a gravity well, kind of the same thing. So this would extend down. All right, so let's take a look at a function that's a little more. Let's take a look at my email.
Just like Gmail.
Yeah, that's the Gmail function.
Natural log of Gmail.
How about f of xy? Yes, this would be number 5. I think so.
Gosh, I hope so.
Don't need the sash, dog.
Y over x squared plus y squared.
Don't we have a hole because it's 0, 0? 0
What?
is 0.
Well, what happens when as xy approaches 0, 0? 0, 0 over 0, we get an indeterminate form. All right, so for a function like this, we have to show that the limit is different along two different paths. So let's look at the path along y equals 0. So along the line y equals 0, so along the x-axis. What is our limit going to be? We get 0 over x squared, no matter what x is.
0.
0. Our limit's going to be 0. And then we want to be clever with this one and pick another path where if I plug in some value for either x or y, I get some cancellation in the numerator and denominator. Any idea what a good path would be? What is it, Sam? Y equals x. Let's look along. Y equals x. So when I plug in y equals x, I get f of xy equals x over x squared plus x squared, which is x over 2x squared, which is 1 over 2x, and the limit as xy approaches 0, 0 is what? Undefined. Does not exist. So along one path, our limit is 0, but along a different path, the limit is undefined. So this one is not continuous. At 0, 0. Any idea what this tells us, that the fact that the limit is something along one path but undefined along another path? What's going to be happening there?
It's going to have some sort of fold.
As a fold something, but it's going to be like walking along a really steep canyon, right? You can walk along a level path, but it's really steep here and it's really steep there. So let's take a look. There we go. So I could walk along here, and my function value is 0. But if I walk along here, I'm going way, way down to negative infinity, and along here I go way, way up to positive infinity. So we get this limit that doesn't exist. Even though we have a limit along this path, we don't have a limit along the other path. So usually for those kinds of problems, the form of the function will suggest the substitution that you want to make. Whoops, my email again. So the form of what you want to do is substitute some function in there to let you cancel one of the variables in the rational function. So you end up with something like this. Yes?
So let's say that we had this same kind of situation, but it didn't end up to just go down to something where it's like 1 over 0. Would we be allowed to use L'Hopital's as long as it's in one
Yes,
variable?
so if you have one variable, if you had something like this that's a single variable, then you can use L'Hopital's to reduce it more. Right. So for example, if you had something like f of xy is natural log of x squared plus y squared over x squared plus y squared. I would say let w equal x squared plus y squared. Then you have f of xy is just natural log of w over w.
And then you can start using.
And then you could use L'Hopital's rule and you differentiate with respect to w. And that's okay.
And that's acceptable.
That's
It's
acceptable.
just if it's in more than one.
Right.
you can't be saying that.
So for this one, that substitution would be nice. Sometimes they're not always that nice, and then you have to pick a nice pick a nice path. All right, questions. All right, if you have a piecewise function, this is just a reminder. Remember that a piecewise function, in order to be continuous, your function value has to equal your limit. So if you get a piecewise function and it defines a function value at a particular point, and that is not equal to the limit at that particular point, then the function's not going to be continuous.
What does that even look like in a
What's that?
What does that even look like? Because like on a two-dimensional graph, you have like your curve and then a little mark that says this is here and then a point somewhere else. What does that even look like in 3 dimensions?
Well, you would at various values of x and y, you'd have some surface, but at one particular value of x and y, you would have a value from another surface. So you'd still just have a point.
So it would just be a point. So there's
Right.
No, so there's just no surface. It's no longer a one.
Well, it depends on if you're sticking the point in where there's a hole in the surface, where there's a problem in the surface, or if you're sticking it somewhere else. Right. All right.
What? Excellent. Why did your piecewise function there?
No, but that's why it is the S. Each consonant is a combination of vowel.
Hey, I just asked
What?
President Eagles fan.
What?
Kyle.
We tell
Did you
them
ever
better.
meet Kyle?
No,
Who's the Eagles quarterback?
I think it's no. I think we should change it. Let's start a petition. Get rid of W and make it
Capital W looks like lowercase w.
what?
All right, there you go.